Okay, so we're gonna be doing our Unit 12 practice exam. So this is gonna go to a little bit of an intro to statistics and data displays. This one's pretty easy, I think, so let's go through it. Going to number one. So here's a table that shows a list of 20 of the largest springs in Florida. Freshwater springs. They discharge a bunch of fresh water because it's like an underwater river getting spit out into these springs. And this is the region where they live, the district. And for here and here, I don't know if you can see my mouse or not. So for here, these are the districts or the water district, right? So, and then this is the actual number of cubic feet per second of water. So this gives us a numerical value of how much water is getting spit out this thing per every second. So, so let's kind of look at the first question, and we're going to select all the displays that can be used to display the data set of the water districts. The water districts. Okay, so let's look to see what type of information the water districts is. Right, the water districts is categorical. It's categorical. Right? So we really only have, let's see, how many water districts do we have? We have Northwest Florida, 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 and Northwest Florida. Okay. And now let's look at Southwest Florida. Southwest Florida, Southwest Florida, Southwest Florida. Oh, is there any more Southwest Florida? I don't see any more. Okay, now let's look at the St. Johns River. Let's do purple for St. Johns River, right there and there, and there, and it looks like it's all that. Then we have the Swanee River. We'll make that green. The Swanee River, 2, 3, 4, 5, 6. Okay, so now this kind of like helps us see the different number of data things that we have, right? So what is our n value? I guess it's not really answering that question, right? But so this shows that we have these various uh, districts for disregarding the discharge rate for all these at this particular moment because it's only asking for the water districts. Okay, so um, what would be would a box plot work for this? No, a box plot won't work for this. Let me change to red or a different color. Would a box plot work for this? No, a box plot does not work for this because it doesn't have any numerical data to deal with. Right? Box plots are usually only for numerical data. Okay, could we use a bar graph? Yeah, we could use a bar graph. We'd have like an X and a Y, and then we would count the number of like three purples, like three purples like that. How many reds are there? 1, 2, 3, 4, 5, 6, 7, 8, 9 reds. 9 reds, something like that, and so on and so forth, right? Oranges, yeah. So you get the idea. So a bar graph, yeah, a bar graph would work. Will a histogram work? No, histogram. We need to be able to put stuff in bins with like numbers and ranges. We don't have numbers and ranges in the in the water data districts, so that doesn't work. Neither will a line graph, right? Because line graph is used for bivariate numerical data, and that's not bivariate numerical data. We have bivariate data here, but both categorical and numerical. Okay. Will scatter plot work? Nope. Again, that is two bivariate data ways. A circle graph. Yeah, we sure could use a circle graph, right? We could, or a pie chart, right? And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 20 of the total, and we could split this up in 1, 2, 3, 4, 5, 6, 7. So 8. Northwest Florida was like 8 of the 20. So 8 over 20 is 8 over 8. Well, I should be able to do this in my head, but I'm not gonna. That's 40%. Okay, so 40% is just a little bit less than 50%. It's like that. So this would be Northwest Florida, and so on and so forth. I guess I'll do the green 1, 2, 3, 4, 5. So that is 5/20ths, which is 1/5. That's 20%. Right. So our green one would be the Swanee River. Would be 20%. Swanee River. That's 20%. Yeah. So and so on and so forth. Right. You can continue this. Right. So yeah, a circle graph would definitely work. Will a stem and leaf graph work? No. Stem and leaf graph doesn't really work because I'm not using numbers. This is for numerical data only. Could I use a frequency table? I sure could use a frequency table. In fact, if I wanted to change these and put the percentages in here, that's what I would use. And then I would take that frequency table and turn it into my circle graph. So yeah, a frequency table works good. And so does a relative frequency table. That's actually what I just described. A frequency table would be the number of this is a district, right? This is the number of in the Northwest Florida, and it was like, what was it, like 9? 1, 2, 3, 4, 5, 6. It was 8. It was 8, right? And we do the same thing for the Swanee River, which was 1, 2, 3, 4, 5, 6. So that's 6, and so on and so forth. And that would give me. But then if I divided all of these by 20, it would give me the percentage in decimal form. All right, so yeah, that would be the relative. But a line plot or dot plot doesn't work, right? Because it's straight line. And these, I mean, not a straight line, but these are numerical. These are not numerical. This is categorical data, right? So here's another question about that: is categorize the data set. Well, this data set is numeric. It's both numerical and categorical, right? And it has, if we're going to look at those individually, there's univariate data, right? It's hard to combine. I mean, you could take this information and turn it into using your relative frequency table, right? For your different, and then plot those two numbers. But as it is right now, it gave it a two different set. It's like two tables combined into one, right? These variables don't necessarily, like, these aren't really variables. These are categories, right? You can turn these categories into a variable by using a data table, right? And then do something with that information. But as it sits right now, this is a univariate data. Okay. All right. So here is this one. Right now it's asking us for the average discharge in feet per second. So now we're focusing on this. Okay. This and this one. Okay. We're not paying any attention to this chart, to right here. We don't care about that. Okay, so now we have just a set of numbers, really, right? And each one of these represent the amount at each of its corresponding location. So what would be appropriate for this one? Could we use a box plot? That's the one that looks like this, right? With our median right here, our lower quartile right here, our upper quartile right here, and then the maximum, the minimum, and the maximum. Yeah. So could I figure out all that information with these numbers? You betcha. I sure absolutely could. So I'm going to make this one yes. this one is indeed a box plot will work. Will a bar graph work? No, not really, because I don't have any like categories um, to to make the bar graphs into for each bar, so that won't work. Will a histogram work? Yes, it will. A histogram will work. I could identify the different ranges. There's 20, so the square root of 20. Let's see, I don't know what that is. Let's see, 20 square root. It's like 4.5, so I could use a bin that is has 4 numbers in it, or a bin that has 5 numbers in it, and I'd have a little bit of leftovers, right? But the number of bins that I would use, and I would drop them in there based upon the range. The minimum is it's like 148, and the maximum is 2,000, right? So the range between that is 2,000 minus 148. 2,000 minus 148. That's on 1,852 is the range. Range is 1,852, right? And if I divided that into 4s for each bin, let's divide that by 4. It's 463. So 463 would be the range of each bin, right? So it would be 2,000 minus 463 minus 463, 1537. So that would be the only one in the first bin. All right, 1537 minus 463 would be 1074. So everything from 1074, from 2000 to 1074, I wouldn't have anything. I'm going to subtract 463 from that. So anywhere from 1074 to 463 would be my second bin. So my second bin would be, or my third bin, because bin 1, that's the red one. Bin 1 has 1 in it. Bin 2, didn't have any in it. Bin 3 had, let's see, anywhere from 1074 all the way to 611 inclusively. So that one would have 3 in it. I take 611 and I subtract 463 minus 463, and it'll be 149. For everyone from 611 to 149 would be bin 4. So bin 4 is, let's see, so 611 to 462. It only has 2 in it. And then bin 5 would be 149, 611 to the bottom. So bin 5 would be bin 5 equals all of these from here to here. So most of them are, that's 1, 2, 3, 4. There's 14. It's 14. So my histogram would look something like this: 1, 3, 2, 14. It would look like that. That's what my histogram would look like. Okay. So yeah. Anyway, histogram works. Line graph. Will line graph work? No. No, it will not, because I'm not comparing 2 sets of bivariate numerical data. All right. Will a scatter plot work? No, it won't work. I need 2 sets of bivariate data. Will a circle graph work? No, I don't have any categorical data. Okay. Will a stem and leaf work? Yeah, stem and leaf will work. All right. I can have my stem as as 1. Let me delete all of this stuff here. So delete. Okay, so the stems could be starting at 1, right? Starting at 1, I would have probably we'll start at 9. This is what I would do with that one. I would start at 14, right? My stem in my leaf, right? If I had 14, my leaf would be 8. If I had 15, my leaf would be 0, 2, 8, and 9. 0, 2, 8, and 9. If I had, 16, it would be just 4. 17 would be 4 and 8. 4 and 8. And so on and so forth. And then that would show me the distribution. So yeah, I can have a stem and leaf graph. Frequency table. Yeah, a frequency table could work. I don't think it would be real effective, but let me think on that one for a second. No, the key says a frequency table would work, but I don't think so. I don't think a frequency table would work, at least not very effectively, because you don't have repeated values. So yeah, a frequency table would not work, nor would a relative frequency table work. But a line plot would work, right? So a line plot, we have numerical data, and so we would just start plot a number line between 148 and 2000, and we could plot all the dots on here, but I don't have any repeated values. So I could make one, but it wouldn't be very effective, right? So there's that. You could use it. Doesn't mean it's the best effective one. Okay. All right. So here is this one. Okay. A researcher surveys 2006 public and private school students. That is my N value, the number of data points. Okay. Between these two things, that doesn't matter. That's all just information in there sent to give you a distraction. Okay. And they said the survey found that 86%, so 0.86, agreed with the statement. The margin of error is plus 3.7 and minus 3.7. So 86% minus 3.7 and 86% plus 3.7, right? And on each account, you can see 86 divided by 3.7 equals, and we're going to subtract, why did I divide it? It should be 86 minus 3.7, and that's going to be 82.3. 82.3%. And all the way to up to 89.7%. Okay, so now I'm gonna put these in decimal form. So 0.8237 to 0.897. Okay. There's no 7 here. What am I doing? Okay, so 0.823 all the way to 0.897. So what is 0.832% of 2006? I'm going to do on my calculator, 0.823. That's 82% in decimal form times 2006, and my bottom end comes out to 1650.0 0.938. So 1650.938. And what I'm going to do is round this number to the nearest number. So 0.9 rounds up to 1650. Okay, and then I do 0.89. This is not a minus, this is a 2. Okay, so 0.897 of 2006 equals 1,799, and we're going to round that to 1,799.382, and we're going to round that down, because that's a 3 and not a 5 or greater. We're going to round that down to 1799. 1799 students. So that is the range based upon my margin of error of 2,006 people. And the median of that was 86%. Okay. All right. So here's a very similar thing. Right. There were 47,851. It's more early morning still. That's my n value. That determines the likely degree of the statement. If I make a mistake, I try to figure out what went wrong. All right, so this is using the same information from up here. It's not a really good question, so I'm going to fix it before you guys take the test. Right, but you're using the 0.823 and the 0.097 range from question number 4. And so that gives that we're just going to multiply 0.823 times that, which gives us a little bit over 39381, enough to round down to 39381. And then if we're going to multiply by 0.897, it'll be rounded to 42923 students. So be careful how this is worded. Make sure you're answering what they're asking. Sometimes you have to figure out the other percentage with the margin of error. So if they had like 86% of the students said they agreed with the statement, that means that 14 plus or minus 3% disagreed with the statement. Okay, so we're going to move on to this one. All right, so here is the daily cost of a healthy diet. Government, the mean is the average is $3.70. The median is $3.60. The minimum is $2.20. Let's do it like this. Okay, so and the maximum is $6.21. The first quartile is this. The second quartile, the third quartile is this. Lower and upper quartiles, and a standard deviation is for the n number of countries. All right, so let's make a little table that shows what we actually have going on here. All right, so we have a maximum, a minimum, and then everything in between. All right, so the maximum and the minimum, the mean is a little bit higher than the median. And then the first quartile is going to be lower. So the lower quartile, and the upper quartile, and then standard deviation. Standard deviation is all these different values. Okay, so we can make a cool little table here. that helps us identify what is going on. All right, so the maximum was 621. Maximum was 621. The upper quartile is $4.13. The mean is $3.73. $3.73. The median is $3.70. The median is $3.60. $3.60. The lower quartile is $3.19. And the minimum is minimum is $2.27. $2.27, and the standard deviation is 0.075 cents. Oh, no, just 75 cents. Okay. So what is standard deviation, in case you forgot? It is the average distance or deviation from the mean, right? So say, for instance, I had a line graph. Do I have a line graph? No, I don't have a line graph. But say I had a line graph, okay? And I have a scatter plot like this, right? And over here, it's a straight line. It's supposed to be a straight line. And it represents the average. It represents the average of all these numbers, right? As it goes up. Okay. The standard deviation is the average distance of each one of these points from the mean. Okay. So that's what a standard deviation is. If I took the distance of all these things, I added them up, and I divided by the number of data sets, that is what standard deviation is. Okay. So let's see what the question is asking. So over here, it looks like they made a bar graph for the maybe that's a histogram. It might be a histogram. Looks like it might be a histogram. Here is a box and whisker plot, right? And here is a dot plot. Yeah, this is definitely a histogram. Okay. All right. So pick the right options from above. All right. So the measure of the center best summarized by healthy data or by a healthy date is the what? Well, do we want to use the mean or do we want to use the median? Remember, if this is a pretty good bell curve until this gap right here, right? That gap has these 5 countries skew the data, right? And because the data, if like it didn't have that gap there, we had a nice little bell curve like this, right? But then it goes like this, right? So that this data makes us say, well, the median, because the display, because the what display, the Y display, right? Because display Y, right? So display Y shows us this and this, right? That, right? The data is skewed by this maximum. Okay, so I would accept X, Y, or Z here, Y or Z here, but Y is the better answer, right? Because it shows that this data is affected. Like, look at the size of this box, and that was stretched because of how far out this was. Okay, so that shows is skewed. Data, it shows that the mean is influenced by these outliers right here. Okay. Now, some data displays can be used to show the shape of the data is something which indicates that the something is the best measure of variability. Excuse me, variability. Right. So all three of these show the variability. Right. So here displays X, Y, and Z can show the shape uh, is skewed, right? It is skewed. SKEWED is skewed, which indicates the interquartile range. The interquartile range is the best measure of variability, not the standard deviation, because the standard deviation is thrown off by this. And what is the interquartile range? Well, from here, this looks like 2, and it's from this the difference between here and here, right? Oh, excuse me, from here and here. It's the difference between here and there. That's the interquartile range, and the difference between that's wrong. The interquartile range is the distance between here and here, right? Because so if I take the distance between here and here, the interquartile range, right, is a better approximation of the majority of the data, discounting these outliers. So that's better. Okay. All right. So that's that one. All right. So here's a table that shows the BMX bike can be jumped, can jump, and the weight in pounds of the bike. So this is how high it'll jump, and this is the weight of the bike. Okay, so this is just a plotting game, right? So at 9.60, you find 24. So here is 23. Here's 24. So right here, 24.5. So right there must be 24. Can I make this bigger? Yeah. Yeah, so right there is 24. Maybe I make that smaller. Make it like right here. So right there is 24. Okay, at 9.7, it should be 23.5. 9.7, 23.5, right there. Okay, and then at 9.79, it should be 23. 9.79, it should be 23. So this is 22.75. So this is 23. 9.80 and 22.5, 9.80 and 22.5. This is 0.75, so that's 0.5. Right, and you can see that this process will just continue until I can connect all of the dots. Right, so you just continue that process. It's pretty straightforward. All right, so here's another one of these fill in the blank ones. Controlled study, cell phone usage between these people and Wuhu City. The study found that smartphones were smartphones and poor sleep quality were correlated with a correlation coefficient of 0.96%. Remember that correlation coefficient way back from one older unit? Is a number that indicates how strongly, like in a scatter plot, how strongly the data is grouped together. Right. So say I had something like this, and that was the two variables that they used for the study, and I had like dots like this. Right, that would have a very high correlation coefficient, closer to 1. The closest it gets to 1, the more of a linear, or the less the difference between these points and the line are, right? If I had, if my points were like this, right? I would have a lower correlation coefficient further from 1, okay? Because this is positive, the correlation coefficient is positive because this is a growing function, right? The correlation coefficient is positive. If it was a decaying function or a decreasing function, it would be negative. Okay, so anyway, that was just a real quick review of all that stuff. So the correlation coefficient, knowing that, let's answer these questions. Okay, they said, so the correlation coefficient shows that something is what? So what is this? So it shows that, what is this study trying to say it is concludes? It said that addiction to smartphones is correlated. It is correlated. It is correlated, right? There should be a with there. Oh yeah, it is correlated. Oh, that B's right there. Correlated with cell phone use. So there is a strong correlation between cell phone use and addiction to smartphones. Okay. It also says that the researchers, because of this, the researchers can claim that cell phone use causes addiction to smartphones because it was a controlled study. Okay, so that is how that whole thing is summarized. Okay, all right. So here is a survey that has n value of that many students and a relative frequency table that shows the percentages of that. All right, so I could figure out the numbers. I guess I could do that. All right, so if I want to bring this up here, and I want to put the actual numbers in, but do I need to do that? No, I don't need to do that. Not in this question. So it says drag and drop. This is a drag and drop, right? So let's take a look here. Can I make this? No, I don't think I can. All right, so individual sports teams, I'm going to call that as individual sports team. That'll be red. All right, that's the greatest one. Okay, so this is the biggest one right here. This is 42%, and it's individual sport teams. Okay, and I have this art, which is 36%, and this is the second biggest value, 36%, and this is art. That's art, music or dance. It's all art. Okay. And then we have this. Let's use this teal color. No, it's not a teal color. This is the teal color. The computer gaming. I'm just gonna call that computer programming, right? And it's the 12%, which this is a little bit bigger than this one. So this is a 12%, and it's computer programming. And then the remaining one that we have is this orange one here, debate team, and or chess club, and that's 10%. That's 10% debate team or chess club. All right, so that's all you have to do is drag and drop these things for this one. Okay. Now, what is going on here? I think I need to delete this one. Determine the number of respondents. Oh, no. It's a very small question. Determine the number of respondents who are likely to perform in art or dance, right? So we're using this 36%, which is 0.36 multiplied by 2,450. So with the calculator, I go 2,450 times 0.36, and I get 882, right? So 882 students. All right, now here we got this one. It's asking for original data. How many sectors labeled as 10% or less, and how many labeled 10% or more. Okay, well, first I got to figure out how many I have total. All right, so I'm going to add all of these and all of these. All right, so I'm going to add those 637 plus 196 plus 196 plus 245 plus 98 plus 392 plus 490 plus 49 and plus 147. So my total is 2,450. And so 10% or less. So anything 10% of this is 245. So anything less than 245. Let me change color. So anything less than 245 is 10%. Because how did I know that? Well, I took 0.10 and I multiplied it by 2,450 and I get 245. So anything less than 245. So that is less than, well, this is 10%. It says 10% or less. So that is 10% or less. That is 10% or less. And these two are 10% or less. So I've got 1, 2, 3, 4, 5, 6. So 6 of these have that are labeled 10% or less. 10% or 6 of those are 10% or less. And the remaining 3, 1, 2, 3, 1 are 3%, more than 10%. Right. So that is that one. I'm going to go back and fix. I guess I don't need to if you guys are watching this practice video. Just recognize that this one was just missed some information. So in the exam, I'll take the one that's similar to this and change it. And everything else should be pretty straightforward. And I hope that this helped you.